Let's go.
Okay, so earlier we were talking about the factors influencing the resistance. So in the factors there influencing the resistance, so we just gave there as the length, other one is the area of cross section, other one is nature of material, and all these three you have learned in the earlier classes. And here we talked about the temperature. So how this temperature influences this resistance? How it influences the resistance? So when the temperature increases, the collision between the electrons and ions or atoms of the material increases. That means the agitation increases. So when this collision increases, so there what happens? The time taken between the collision decreases. The time taken between the collisions, the average time taken between the collision decreases, and there will be change in the drift speed also. So anyways, it is an influencing your resistance. So when it is influencing the resistance or the resistivity, so here by this, when this collision increases, you can say that the conductivity decreases and thereby resistivity increases. So when we say that the resistivity increases here, so initially let the temperature be T0, and if the temperature is raised to T, there will be change in the resistivity. And if we just take the resistivity at this temperature is rho T0, and here it is rho T. So now here the relation, how we can find out the temperature, how we can find the resistivity at this temperature is given by the formula rho T is equal to T0 into 1 plus alpha T minus T0. So using this formula you can find out the resistivity at this particular temperature. Here alpha is a constant, and this is constant for a material. For a material, the value of alpha is constant. And what is this called? Means it is temperature coefficient of resistivity. Temperature coefficient of resistivity. So this is your alpha here. And we know that from the expression R is equal to rho L by A or something else here. So R is proportional to rho. So R is proportional to rho. Because R is proportional to rho, we can change this expression as resistance at T will be equal to resistance at T0 into 1 plus alpha into T minus T0. So like this we can find out the resistivity at a particular temperature. From this we can understand that as the temperature is changing, the resistivity or resistance is also changing. So like this factor is influencing this resistance. Okay, so just pause the video and take the screenshot of this. And after talking about this resistance, and we just know, we came to know the factors influencing the resistance, and what are the units for that, and the formula for it, and in Ohm's law, from the Ohm's law we have derived this. And here one more property is that is the conductance. And this is the conductance is nothing but it is the reciprocal of resistance. Conductance is the reciprocal of resistance, and this is denoted by G. So G is equal to 1 by R. because it is the reciprocal. So we can write the units for this. It is for resistance it is ohm. So it is ohm inverse, or we can give the symbol as the symbol for this is omega. We can write the symbol for this as omega inverse. And sometimes it also can be sometimes we can see it as, instead of writing ohm inverse, they will be showing it as MHO. There is also, because it is just as the inverse of it. So this is one of the property of the material, which is reciprocal of the resistance. And already we know about this resistivity denoted by rho. And we just understood this from R is equal to rho L by A. So here is your resistivity. And here we just give these units for this as ohm meter and the symbol as omega meter. And the reciprocal of resistivity is conductivity. The reciprocal of resistance is the conductance, and reciprocal of resistivity is conductivity, and this is denoted by sigma. And sigma is 1 by rho. It's reciprocal. So when I write the units for this, the reciprocal of this is ohm meter inverse, and ohm inverse and meter inverse. Or I can write like this, omega inverse, meter inverse. And there is one more unit for this conductance. It is, the SI unit is Siemens. Ohm inverse is Siemens. So I can write this as, now instead of this ohm inverse, Siemens meter inverse. Okay. So the SI unit of conductance is Siemens, so became conductivity is Siemens meter inverse. So these are some of the important properties along with the resistance. And you have to know about this resistivity, already we talked about it, conductance and conductivity. Alright. Now, in the earlier session, we talked about the free movement of the electrons, the mobility or the movement of the electrons, free electrons. There, you have taken a conductor and you have applied a potential difference V, whose length is L, and the area of cross section is A. Now if it is submitted to the potential difference V, here electric field is applied. And from this we should understand the very two important terms here. So when the electric field is applied, the free electrons gets the acceleration due to the electric field and they start moving. They get accelerated. And after getting accelerated, they collide with the ions of the atom, ions or atoms of the conductor, and again they lose the energy and the velocity gets reduced. And because of the applied potential difference, again it gains acceleration and the velocity increases. So this process continues. So here in this case, a stage comes where the acceleration becomes zero. And we said that at that stage, the velocity of the free electron, the average velocity of the free electron is said to be the drift velocity. The average velocity of the electron is said to be the drift velocity. So here, once again I am repeating here. So when the free electrons are, before applying potential difference, they are at random. After applying potential difference, due to this applied electric field, they gain energy and they get accelerated. Because of this acceleration, they collide with the ions or atoms of the conductor. After collision, they lose some energy and again the velocity decreases, and this process continues, and at a particular stage we can say that the acceleration becomes zero, and at that time the average velocity of the free electron is said to be the drift velocity. So we understood that in earlier session, and it is denoted by V. And here the important thing is during these collisions, So between a collision and a collision, a time interval is there. So the time elapsed between the collisions is called relaxation time. Relaxation time. The time elapsed between the collision is relaxation time, and it is denoted by tau, a Greek letter tau. It's not tau, it is tau, T-O-U tau. Okay, and it will be in the order of 10 power minus 14 seconds. It will be in the order of 10 power minus 14 seconds. The meaning of this is, in these 10 power minus 14 seconds, the electrons are relaxed within this time. That means here I told you, between this time, the time interval will be in the order of 10 power minus 14 seconds. In this time gap or interval, the electrons are relaxed, they are free from collisions. So that's why this time is called as the relaxation time. Okay, now after understanding this relaxation time, one more important term is there, that is a path, mean path. So here, so now between the particle, during these collisions here, it is mean path difference. It is denoted by lambda. So the distance traveled, the average distance traveled between these during this relaxation time or between the collision and collision is shown by this lambda. These are the two important terms what we have to understand here. And after understanding this, we'll move on to this next session. Now pause the video and take the screenshot. And now, after understanding this mean free path, lambda, and we understood this as the average distance between the successive collisions is lambda, and the other one is tau, that is relaxation time. Relaxation time. And we know that this is the time elapsed between the average time elapsed between two successive collisions is the relaxation time. Now here we are going to derive the relation from between this using this lambda or this tau and drift velocity, and connecting this current and current density and some other things. And here we are using this derivation, we are going to get one other form of Ohm's law. So now we just can know it V is equal to IR, and we'll get one more form using this derivation here. So for this, after understanding all these things, now let us go with the derivation here. Now let us take a conductor of length L, area of cross section A. Okay, now if this is if a potential difference V is applied across its ends, now an electric field is developed in the conductor of E. So now if the electric field is E for the conductor of length L, then we can write it as E is equal to V by L. Now the conductor is applied by a field E is equal to V by L. So due to this applied electric field E, the electrons or the free electrons get accelerated. Already we know about this, get accelerated. And here, because of this, the average velocity will be existing. So if you want to talk about this velocity here, let us take the instantaneous velocity, the velocity at a particular time. So instantaneous velocity, let us denote this by v. Instantaneous velocity v, due to the applied electric field E. So now, if I just take dv by dt, so here you might have understood that we are going to get acceleration here, isn't it? So acceleration. So now, how to just give this acceleration means we will use this expression F is equal to ma. So what is F here? F is equal to, for the electrons and the applied electric field E, F is equal to QE. What is Q here? Charge. What is the charge of electron E? So F is equal to QE using this electric field E. What is the charge of the electron E? So F is equal to EE. So it is E M, mass of this free electron, and A is the acceleration. So A is equal to E by M. So now we got it as, so now instead of writing A acceleration here, just I am writing here E by M. So this is the acceleration acquired by the electron due to this applied electric field. Due to the applied electric field, the free electrons in the acceleration. But when they are moving here, they undergo the collisions. That means, due to these collisions, the opposing force will be acting on these free electrons. So now, because of these collisions, opposing force acts on the free electrons. Opposing force acts on the free electrons. If we talk about this opposing force here, so here also I use F is equal to ma. F is equal to ma, and this F is equal to m. A acceleration means it is velocity by time, and here m v. So here, because of the collisions, here this time will be changed to tau. So here, because of the collisions here, the time interval between the collisions, the average is taken as the relaxation time. So I use that mv by tau. So now, so here you got this acceleration as v by tau here. So now, so this is the acceleration developed due to applied electric field, and this is after the collision. So now what will be this net acceleration acting here means it is E by m minus v by tau. Okay, so this is the acceleration developed due to applied electric field. So this is due to applied electric field, and this is which is due to the opposing force because of the collisions there. And here, after understanding this here, so this expression we got it here, and a stage comes where this opposing force will be balanced by the applied force. So a stage comes there. I can write here. A stage comes, applied force get balanced by opposing force. So when the stage comes there, applied force get balanced by the opposing force. So that means here the net acceleration becomes 0. So that means here the net acceleration become 0. isn't it? So this I can give an explanation here for this. So if this is the applied force and this is the opposing force, if they get balanced, what happens? This E by m is equal to V by tau. So if these two are equal, so this becomes 0. So the net acceleration becomes 0. So the net acceleration becomes 0. Already we know that when the net acceleration becomes 0, the velocity acquired by the electrons, free electrons, we will be calling this as the drift velocity. We will be calling this as the drift velocity. So from this we understood that when the acquired velocity, when the what you call it as the net acceleration becomes 0, that means dv by dt is equal to 0, then the velocity is said to be the drift velocity. The velocity is said to be the drift velocity. So now we came up to the just giving the expression up to here. V is equal to, we got V is equal to Vd, right? Now, up to here, just pause the video and take the screenshot. We'll go with the okay. So we understood that at dv by dt is equal to 0, then your velocity is called as the drift velocity. Okay. Now we understood that here this accelerating force is equal to the opposing force. When with this dv by dt is equal to 0, this is the condition here. So what is the accelerating force here? It is accelerating force is given as F is equal to ma, and it is m. A is it is E m a. So accelerating force is, it is E capital E. Opposing force, it is it is mass into acceleration, and this is acceleration is, it is v by tau, isn't it? So m v by tau. And when these two are equal, that means if it is balanced, we can replace this v with Vd. So E is equal to m Vd by tau. Now we want the expression for Vd, drift velocity. So drift velocity is equal to, taking all this to the other side here, it is E tau by m. And you can write this expression as Vd is equal to E tau by m into E, because this is constant and this is constant and this is also constant. So here the charge will remain constant, relaxation time will remain constant, and the mass of the electron will remain constant. Only the change will be with this electric field, applied electric field. So from this we understood that if these are constant here, Vd is proportional to E. That means from this we have extracted an important thing. Drift velocity is proportional to applied electric field. Okay. So from this we extracted one important thing, and one more here. We set this as a constant. This E tau by m is constant, and this constant is called as mobility of free electron, and it is denoted by mu. Okay. So the E tau by m is constant, and this is called as mobility of free electron, denoted by mu. Now I can write this expression as Vd is equal to mu E. Now we got the expression in terms of drift velocity, mobility of the electron, and electric field. Okay, and you just have to remember the formula here. The mobility of the electron is E tau by m. So Vd is equal to mu E, right? Now, already we know the formula for the drift velocity. Vd is equal to I E n A. Sorry, I is equal to n E A V D. This already we know about this formula. I is equal to n E A V D. Already we have derived this earlier. So from this expression, just we'll include all these things and we'll extract whatever we require here. So now I am using the expression I is equal to n E A. So instead of Vd here, so I am going to just substitute this using this I am going to substitute here. So it is E tau by m E. So n E and E square A tau by m into E. Already earlier in the beginning I told you E is given by V by L, because potential V is the difference applied a conductor of length L, so it is replaced with V by L. So now I got the expression as I is equal to n E square A mu it is tau by m into V by L. We know from our Ohm's law, V by I is constant, isn't it? So from the Ohm's law, V by I is constant. Okay, so now bringing this into that form here, so V by I, taking it here, so it becomes V by I is equal to so what it becomes here, so this m L, this comes this side, this denominator goes to numerator here, m L goes here, and this value here comes to the denominator, that is n E square A and tau. So V by I is constant, and V by I is constant, and that constant is nothing but V by I is equal to R. This R is nothing but the resistance. Already we know about this. And here just comparing these two expressions here. So this resistance is equal to this value here. So resistance is given by m L n E square A and tau. Okay, so now using the relaxation time, we can find out the resistance, that is R is equal to m L n E square A and tau here. And from this you can extract one more important thing here, that is already we know R is equal to rho L by A. So now here L is there and A is there. Just bringing them aside here, so it becomes R is equal to m L n E square and tau by A. And we know that this mass is constant, n is constant, E is constant, rho is constant. So this is a constant value here, and it is in the place of this rho. So now I can write it as rho is equal to m n E square and tau. So this rho is the resistivity. So now we got the resistivity as rho as m by n E square and tau. What is the reciprocal of resistivity? Conductivity. So that is sigma. Sigma is 1 by rho. That means just inverse. So it is n E square tau by m. This is the formula for the sigma, that is conductivity. Okay, now with this we find a very important use here. Now from this, using this expression once again here, I is equal to n e square a tau by m v by l. So instead of this, so I will bring this a this side here. I by a is equal to n e square. Already taken that side. This 2 remains 2 by m. This v by l. V by l is nothing but e. So it is e. Okay. What is this I by a? Already we have just talked about this in the earlier session. It is I by a is nothing but current density. Current density J. Current density J. So now instead of I by a, I can write as J, and this is n e square sigma by m. Where you have seen this here. Just look at this conductivity here. Sigma. N e square rho by m is sigma. So it is sigma and e. So this is what you have extracted from all these things. What we call it as this. This is, we can call this as the other form of Ohm's law. J is equal to sigma E. So of course it is, we have just said that it is the other form of Ohm's law. From this derivation we have derived and we have come across so many things. So here, right from the beginning, if we take, we talked about, we understood what is relaxation time, what is the mean path length, and when this instantaneous velocity will become the drift velocity, when this accelerating force is equal to the opposing force. And from there we just talked about one of the more important, there is mobility of free electron, and we have derived an expression for this. Mobility of free electron mu is equal to E tau by m, and after finding this we just found that Vd is proportional to E. That means drift velocity is proportional to applied electric field. This is an important thing. Drift velocity is always proportional to the applied electric field, and the relation between drift velocity, mobility of free electron, and electric field is Vd is equal to mu E. And resistance, in terms of this resistance, we got it as this relation we got, and resistivity in terms of this we got it like this, and got it to the conductivity, and then I by A is equal to J. So E, and how this J and E are related, J is equal to sigma E, and this is the other form of the Ohm's law. Now pause the video, take the screenshot again and again, and you will find it easier. And most important thing here is, just even though if you don't remember the derivation, try to remember the things whatever I have said to you. The drift velocity proportional to electric field, what is the mobility of a free electron, and what is the other form of the Ohm's law, and what is the formula for the resistance in terms of the, what you call it as, number of electrons and relaxation time, and what is the formula of conductivity, resistivity in terms of relaxation time and number of electrons. Okay, so all these things you just put it on the piece of paper, read it number of times, so you will get what it is, practice. Okay, so that's it for this session. Okay, see you then.